In general, CPUs are bad for image processing. The ability to write hardware description language to customize a processor can greatly improve the efficiency of an image processing technique, such as an artificial neural network. The goal of this project is to capture real-world images and process them using an artificial neural network, or ANN, that demonstrates what the image actually represents. To show that this works, we will be calculating the addition of two inputs in the form of handwritten numbers on a whiteboard. Processing will be done on a Spartan 6 FPGA, and the results will be displayed on a monitor. This is a view of our high-level block diagram. We will be going over the components of our project and explain important components in detail. These are our inputs. We take in a 100 MHz clock signal, a camera signal, and a push-button input. The camera writes its data to block RAM, where it then feeds the artificial neural network. The first component we will look at is the artificial neural network, which decides what digit is displayed in the image. What we have here is a diagram of the artificial neural network, or ANN. The neural network is comprised of nodes that do a logic function on a set of inputs. Since the images that we are processing are 20 by 20, in the beginning we will have 400 inputs. Each of these inputs goes into the first level of 400 nodes. Each input is then assigned a weight, and an output is calculated using these weighted inputs. The weights were determined during a training process developed in MATLAB and then ported over to Verilog. The outputs of the first level are then input into the second level of 25 nodes. Again, each input is assigned a weight and an output is calculated. Finally, the outputs of the second level are input into the last level of 10 nodes. These 10 nodes then calculate a decision and output that decision on the existence of a digit. Each of the last nodes corresponds to one digit, so if the first node's output is high, the image is decided to have a 0 displayed. The weights were chosen so that no two outputs were ever 1 at the same time. So the output is encoded in a one-hot pattern. The next component is the value buffer, which captures the output from the artificial neural network. Here's a diagram of what we call our input buffer. This module takes the decisions from the artificial neural network and buffers them for use by the calculator module. Since the artificial neural network only decides on one value at a time, and we need two values to do an operation, this module basically demultiplexes the output of the ANN to two buffers that act as the operands. The module is a finite state machine made of 6 states. The artificial neural network drives a signal high when the decision for a digit has been made. In state 0, we wait for the ready signal to go high. When it does, we transition to state 1, where we capture the value from the ANN as our first operand. We then transition to state 2, where we wait until the ready signal goes low. This is to prevent multiple captures on the same decision. We also assume that the ready signal will go low between decisions, which is a pretty safe assumption since the ANN takes over 400 cycles to come to a decision. When the signal does go low, we transition to state 3, where we basically repeat this process for the second operand. I.e., we go to state 3, waits for a high signal, state 4 captures the ANN output for the second operand, and state 5 waits for another low signal, where it then transitions back to state 0. Also in state 5, we set an output signal high to tell the rest of the logic that the two operands are ready. The value buffer feeds into a 4-bit calculator that does simple arithmetic operations on the input values. Both the value buffer and the calculator feed into the next component we will talk about, which is the output buffer. The motivation for having an output buffer was simple. We did not want the display to change while the ANN was making a decision. The output buffer uses the flag from the value buffer to know when the two operands are ready. At this point, it stores the current value of A, B, and the current output of the calculator. These values will feed the display logic until the next two operands are ready.
What we have so far is we can threshold an image, and the image is, as we see here, it's just half picture there and half there. So basically, this should go into ANN that we need another probably 15 minutes to finish it up.
But we just don't have time right now.
And
so there's the camera going into the Atlas board, which right now just puts out the entire video.
Yeah, and we can just wait.
So that part. So you can see Zafar moving the image right there. As we press this button, that image will change.
And you can just.
And as you can see, the thresholding happens. Although
yeah, your head is
my
blocking.
Head is kind of in the way. So you can see the 1 is on the screen, and you can clearly make out a 1 in that downsample threshold version of the image. And like Zafar was saying, it's supposed to go into ANN, but
well, another like whatever minutes and we're gonna be done.
yes, unfortunately it's like 11:20 right now, and it's not gonna happen.
Yeah.
So that was like a minute.
I'll get back to coding this.
Okay. Go.
Hi, I'm Mike.
Alright. And this is the second half of our Verilog project. Unfortunately, it does not interface with our first half. So this is the calculator and the VGA output. It's basically what it does is it's supposed to take a 10-bit one-hot encoded signal and a ready signal. And we emulated that with the Nexus board with the switches. Since there are only 8 switches, we kind of left off the first 2.
The 2 MSBs are
Yeah.
just hard coded to
So
zero.
you can see the calculator output. This will be the first operand, the second operand, and the output will be here. So Mike is going to flip. What number is that? 0, 1, 2, 3, 4. Because 0 is the first switch, and then 1 after that, so that's 4.
Yep.
And he's going to press the button to register that. Now, since that was the first operand, you'll see it doesn't change. Now he's going to flip another one, flip like 7. Alright, hit the button. Now you'll see since that's the second operand, it did change. So now it's 4 plus 7 equals 11. Now to show you that we didn't pull any magic on that, I'm going to have Mike do it again with 2 other numbers and show you.
I'll do 1 plus 2.
You'll see it's 1 plus 2, and it didn't change until he had the second number in. Sorry about the sound, there's a server running next to us, and that would have been our entire project, but you can see Zafar is still working on the ANN, and yeah, we could not get them integrated together. Difficulties of this project?
Everything.
Zafar says everything. The camera was a very big difficulty, mostly because it was not able to work on the Nexus board, and there were
Indexing
just
into pixels.
indexing into pixels. It's hard, so yeah, we got so we got stumped fairly badly with this. But yeah, all right. Thanks, guys. This has been Ben, Mike, and Zafar with this crazy demo video.